designer and developer. He has master's and bachelor's degrees in engineering physics from Aalto University. Following the presentation, we'll have a live Q&A with Joel. You can submit questions at any time during the session using the Q&A box on the right-hand side of your screen. At the end of the session, I'll be announcing 2 winners of this live sessions giveaway and today's grand prize winner. Thank you so much for joining. With that, I'll hand it off to Joel for his presentation.
So, hello everyone. My name is Joel Kauppo. I'm a senior product marketing engineer at Nordic Semiconductor. A little bit of background of myself. So before joining Nordic, I worked as a senior software engineer in Bluetooth software R&D, as well as a game developer. So you could say that I'm a developer at heart. So today we will be discussing ultra-low power with advanced Bluetooth LE features and Edge AI on the nRF54L series. Today's agenda will be: first, we'll discuss what are advanced features in battery-powered embedded devices in the modern world. Then we'll talk about real-time asset tracking and especially real-time high-accuracy distance measurement using Bluetooth LE channel sounding as well as ultra-wideband. Then we'll move on to Edge AI running on memory and performance-constrained low-power devices. And then lastly, we'll discuss innovations in power consumption optimizations on the Nordic Semiconductor 22nm nRF54L series. At the end, we'll have a live Q&A. So first, what are some advanced features in battery-powered devices today? So one of the important topics in today's modern world is real-time asset tracking. So some of the use cases for asset tracking on the consumer side are Find My Device type of applications where you attach a tag to your personal asset, for example, your wallet or your keys. And you can use your smartphone to find the device. For example, it could be in your house, somewhere lost, but also it could be left behind somewhere around the town, and you'll be using GPS or other devices to locate your device. Then we have pet tracking, luggage tracking, and vehicular access. On the industrial side, we have medical. So, for example, in hospitals, you could have very costly assets, medical instruments that you want to track their locations. These could be moving from one room to another without anyone personally keeping track of them. So being able to see which room has which device is very important and is saving a lot of time as well as money. Then we have industrial asset tracking, for example, in warehouses. You could track each pallet or packet where their locations are, or whether they are in the warehouse or outside. And we have traditional inventory management, usage tracking, and access control. Then another advanced feature that is becoming more and more important each day is Edge AI as well as machine learning. We'll talk about these in a bit, what they specifically mean in different scenarios. But use cases for Edge AI on the consumer side is health monitoring, hearing aids, as well as wearables with gesture detection. So basically, wearables today, smartwatches, smart rings already cover a lot of features that require AI. For example, we have heart rate monitoring, health metering, sleep tracking, as well as basic gesture detection, for example, for controlling your music devices, controlling volume or television or anything like that. And then we have smart human-machine interaction. And we have also, on the industrial side, we have important use cases in Edge AI in predictive maintenance, fault detection, quality control, agricultural monitoring, like soil and ground, as well as temperature monitoring, humidity sensing, and so on, as well as building automation. So all of these use cases are already using Edge AI today, and the use will be growing in the coming years more and more. Then we have also, for example, advanced security features as well as RISC-V architecture. But today we'll be focusing on the top two, so real-time asset tracking as well as Edge AI and machine learning. So a common problem with the modern advanced features is that they require quite intensive processing, which leads to high power consumption. And as we know, a lot of these devices mentioned here are often battery powered. They could be even coin cell batteries or very small batteries in general. And we want to keep supporting these advanced features as well as keep growing their capability over the years. So we also need to take care of the high power consumption issue. So next, let's talk a bit about the high accuracy real-time asset tracking. So first, we have GPS. That's one of the most common ways we are currently tracking ourselves, but also some assets can be tracked using GPS. Then we have Bluetooth LE, and especially in that area, in the Bluetooth protocol, we have the channel sounding as a distance measurement method using phase-based ranging PBR as well as round-trip time RTT. And then we have the direction finding, angle of arrival AOA, and angle of departure AOD. And in addition, we have ultra-wideband, which is using time of flight with a single antenna, as well as angle of arrival when you have multiple UWB antennas. It's good to note that there are other real-time asset tracking protocols or methods available, but in most cases, the accuracy is not high enough to call high accuracy. So we're discussing sub-meter accuracy. And for example, in GPS, this is the case. We usually get the accuracy of 3 to 5 meters at best. And the most important issue with GPS is that it does not work indoors. It uses satellite technology, which becomes problematic when you move indoors. You have a lot of obstacles in the way of the signal, so you will lose the accuracy. Then in Bluetooth LE, we have the direction finding, which uses triangulation using angles from multiple devices. This is quite accurate, but the main issue here for at least broad market use cases is that direction finding requires specialized hardware, antenna arrays with multiple antennas, which are often quite bulky. And this also means that the existing infrastructure cannot be used as is, so it will require changes. And then in the ultra-wideband, we have inherently quite high power consumption compared to other technologies. So it uses short bursts, which typically consume quite a lot of power. But this can also, of course, be optimized using, depending on the accuracy and use case, you can optimize the power consumption by having the devices idle sleep more. So first, we'll discuss the Bluetooth LE channel sounding ranging method number 1. So channel sounding is a secure, high accuracy distance measurement reaching accuracies of typically 10 centimeters to 1 meter. It is a part of the Bluetooth LE core specifications since version 6.0 in 2024. So it is a standardized method, and it received the first smartphone support in 2025 on the Pixel 10. It works with a single Bluetooth antenna at 2.4 gigahertz band. It also supports up to 4 antennas for higher accuracy. But the key point here is that even with the single antenna, you can get sub-meter accurate distance measurements, which is great for the smartphone support, as typically you only have one Bluetooth antenna in the smartphones. And in channel sounding, we have 2 different methods, actually. We have phase-based ranging, PBR, So the BPR uses up to 72 channels. So what you can see on the right-hand side is we have the initiator. So in a door lock use case, we have a smartphone as an initiator and the door handle or the door lock as the reflector. First, you have the initiator transmitting a signal at one Bluetooth channel, so frequency number 1. You will send the message to the reflector, and the reflector will transmit the message back. And then you will compare the phase difference between these two signals. So you can determine from the phase difference how much the signal has propagated, and based on the phase difference, you can calculate the exact distance that the wave has traveled. Now you know that the Bluetooth band is 2.4 gigahertz, so it is roughly corresponding to 12.5 centimeters. So for this reason, you should run the procedure on multiple channels. So once you increase the number of channels, you get different phase differences on each frequency. Using the information gathered from multiple frequencies, so basically getting the phase differences from multiple frequencies, you can determine the distance accurately. On the left-hand side at the bottom, you can see the equation for the distance. So it's the speed of light c times the phase difference divided by 2 pi times the frequency difference. And then there's the modulus for the speed of light over the frequency difference, which just comes from the fact that the phase wraps over 2 pi once the wave has propagated over the whole wavelength, which is around 12.5 centimeters. But of course, it's good to note that the actual algorithms are much more complex than this, but this sets the baseline for the complexity of the algorithm. Then the method number 2 for channel sounding is round trip time. So this is much simpler than the phase-based ranging, but also a bit less accurate. So in this case, you will just measure the time difference it takes to travel from for the signal to travel from the initiator to the reflector and back again. So the question is, why are 2 different methods used? And especially if the round trip time is not as accurate to phase-based ranging. There are multiple reasons. So one of them is that by combining the PBR and RTT, you get a more secure and more accurate result, as well as that you can use the RTT for a coarse distance measurement and then PBR for getting a more fine-grained and accurate result. But you can also, of course, use only one of them depending on the accuracy needs as well as security needs of your application. Then the method number 2 is ultra-wideband. Ultra-wideband is also secure and high accuracy distance measurement. Here you get typically accuracies from 10 centimeters to 30 centimeters, so a bit more accurate than Bluetooth channel sounding. And this is also standardized in the IEEE 802.15.4z standard. And it's also available in selected smartphones that have ultra-wideband antennas. This works as well with a single UWB antenna. And you can also have multi-antenna support for angle of arrival, so triangulation-based positioning. The key difference to channel sounding with UWB is that it uses short burst time of flight, and it uses 3 different frequency bandwidths. And as the name suggests, the bandwidths are ultra-wide, and the bursts or pulses are very short to mitigate multipath reflection effects and improve the accuracy. But the short pulses and the ultra-wide bands also means that the power consumption in UWB is typically much higher. So to summarize, channel sounding is sub-meter accuracy, whereas ultra-wideband is sub-30 centimeters accuracy. The measurement method for channel sounding is phase-based ranging or round-trip time or both combined. And for ultra-wideband, it is time of flight. The power consumption This is the most important or most interesting part considering today's topic. On the channel sounding, it is relatively low. You can adjust the power consumption by reducing or increasing the number of channels. This also affects the accuracy. So this depends on the environment and use case of the ranging. And in ultra-wideband, you have typically higher power consumption. There's a link to a discussion by uBlocks describing the power consumption differences. Then on the algorithm side, not just considering the protocol, but actually calculating the distance on Bluetooth LE channel sounding usually requires a bit more sophisticated algorithms due to the reason that you're calculating the phase-based distance, which is a bit more complex to calculate, and the fact that you are often using PBR and RTT together, which increases the processing load. Whereas ultra-wideband, the power consumption on the algorithm side is typically a bit lower when you're considering only the time of flight differences, which is a bit more or a bit less intensive to calculate. Both of these are quite secure methods. One could argue that the channel sounding be viewed a bit more secure due to the fact that you are combining the PBR and RTT methods. So next, we'll discuss Edge AI running on low power devices. Now, what is Edge AI exactly? So when we are talking about Edge AI, it means that we are running artificial intelligence algorithms and machine learning models directly on the local devices instead of a remote cloud server. So why do it this way? Why should you calculate or run the AI algorithms locally instead of remotely? So one of the reasons is we have massive amounts of IoT data available today, and processing all of this using cloud requires a lot of bandwidth as well as quite expensive cloud solutions. So another reason is cloud computing cannot really provide ultra low latencies and real-time responses for critical tasks like autonomous vehicles. Then we have data privacy. Data privacy remains an important aspect. So running the AI algorithms locally is more secure and has better privacy control than running algorithms remotely. And then, as mentioned, the cost savings for not needing high bandwidth data transfer or expensive cloud solutions is also important. So what are the current challenges with Edge AI? We have limited processing power. So processing large amounts of data can be very resource intensive. We are running on devices that have constrained memory. The models can be quite large, and we're talking devices that have only some hundreds of kilobytes of memory for storage. So all shavings that can be done in the memory side are important. Then one important aspect is that these are often, again, running on battery-powered devices. And typically Edge AI can be quite power hungry on the computing side. So the problem is that complex Edge AI models need to run on battery-powered devices with limited memory. So more about what is machine learning. We have three classifications of machine learning problems. We have motion detection, typically using a 3-axis accelerometer input. For example, predictive maintenance. Then we have voice, which is typically a bit more complex than motion. The use cases are speech control, voice activation, and there we use sensor fusion. And then we have the most complex, which is vision, real-time image recognition and computer vision. And there the use case is object detection. Now, recently, Nordic has introduced their Newton framework, which produces ultra-small machine learning models. The models are typically less than 5 kilobytes. That's the average model size achieved by the Newton neural network framework. They are up to 10 times smaller and more efficient compared to the convolutional neural networks from competing frameworks, while retaining the same or better accuracy The dynamic growth of deep neural networks is automated until it achieves its maximum generalization ability and accuracy. And they are also 10 times faster on average. So the neuron by neuron approach ensures only the necessary connections are made, which lowers the inference time and removes the need for optimization. What this graph shows, on the x-axis we have the data rate from low to high, and on the y-axis we have the Nordic product range from low end to the high end. Basically, this shows what we can do today regarding edge AI and what we will do tomorrow. So you can see on the left side, we have the LiteRT, previously known as TensorFlow Lite. You can see that on the higher end products, you can do motion detection with the accelerometer. And then with the Newton framework, we can do both motion and voice. And in the future, Nordic products will also have AI accelerator hardware, which will extend the full product range to also support voice recognition and speech detection edge AI. So here we have the comparison between Newton and LiteRT or a gesture recognition case study. Comparing the non-volatile memory, LiteRT would take, with the TinyML framework, roughly 80 kilobytes, whereas Newton would take 5 kilobytes of NVM. Then we would have the device drivers and business logic requiring 93 kilobytes. And these components are shared by both LiteRT and Newton. So as you can see, Newton can achieve 14 times smaller model compared to TinyML with the 43% reduction of the total NVM use. On the RAM side, Newton would get a 10 times smaller model or a 26% reduction of total RAM use, considering the drivers as well as the business logic. In this case, the inference time was 33 times faster on Newton than on the LiteRT, as well as 0.7% higher accuracy. So it can be seen that the accuracy remains similar even though there are big differences in the model NVM and RAM sizes as well as inference time. These were both running on the Nordic nRF54L and both were trained on the same dataset as well as validated on the same holdout set. All right, then let's lastly discuss what kind of innovations in power optimization we have achieved on the nRF54L series that was introduced in 2024. And it's the latest series of ultra-low power wireless SoCs supporting Bluetooth LE, Zigbee, Thread, Matter, among others. It has quite big improvements. So it's using the 22 nanometer process technology instead of the 55 nanometer used for nRF52. This leads to a higher processing efficiency and lower power consumption and a higher transistor density. It reduces the active current by 21% from 3.3 milliamps to 2.6 milliamps and improves the processing efficiency by 62. These numbers are, by the way, available in the blog that's linked at the bottom of the page. Another innovation was that the nRF54L series uses 4 separate power domains, which allows power optimization through independent powering. It has separate domains for radio, MCU, peripherals, and ultra-low power modes. We have a 128 MHz Cortex M33 processor, which doubles the clock speed from the nRF52, which translates into faster and more efficient processing, allowing more idle time. We also have a RISC-V coprocessor, which allows offloading intensive computations to the coprocessor for parallel processing. We have the non-volatile memory using resistive RAM, which allows for faster write speeds and lower power consumption compared to flash, and has also higher endurance. And then on the Bluetooth LE radio design, there were quite major advances. So improving the radio analog design. There was on average 40% reduced power consumption compared to the previous generation nRF52 series. So when we look back to the real-time asset tracking scenarios, channel sounding versus UWB. So on the algorithm side, if we have the algorithm running on the nRF54L, so the nRF54L series supports Bluetooth channel sounding, but not ultra-wideband. So if we consider that both the protocol, so transmission and reception of channel sounding tones, as well as the algorithm processing is running on the nRF54L series. So firstly, we have the 33% more efficient Bluetooth LE radio, which improves the protocol power consumption even further. Then we have the 22 nanometer process node, which has better processing efficiency. And then we have the doubled clock speed of 128 megahertz, which roughly cuts down the processing time by half. So this means that especially important power consumption improvements can be made when the algorithm is being processed on the nRF54L. Then going back to the edge AI issues or challenges, we had limited processing power, constrained memory, and battery-powered devices. So for that, on the processing power, we again have the doubled clock speed, as well as the RISC-V coprocessor and 22 nanometer process technology. These are now improving the capability. We can run more complex models, and we can offload computations to the coprocessor. We can run these computations in parallel, and then we can also run it more efficiently due to the 22 nanometer process node. Then using Newton, we have 10 times smaller models than on competing frameworks, which reduces the memory footprint. And also using Newton, we can get up to 33 times, on average, I would say roughly 10 times faster inference. So these are the improvements we have made to power consumption when running advanced Bluetooth LE features on battery-powered and memory and processing constrained devices. So thanks for listening to this presentation. Next up, we have the Q&A. So I will be answering your questions live. Thank you.
All right. Well, thank you, Joel, for that really great presentation. We've got a lot of interesting questions already in our queue, but I want to let the audience know there's still time to submit your questions. Joel, you ready to answer some of these questions?
Yes, absolutely.
All right. The first one, start with the easy one. Does the nRF54L include a GPS receiver?